Okay. So representing text as numerical data. Well, we need it as numerical data because that's what models work with. So here's some example text, and they are some pretend SMS messages, text messages. The first three messages I'm just storing as a Python list, a list of three strings. The first message is call you tonight. The second message is call me a cab. And the third message is please call me, please. And these are not real messages I've ever sent. We'll say that they're pretend messages. Call you tonight, call me a cab, please call me, please. And I'm going to store them as this object called simple train. Okay. And I just want to use this really simple example before we use a bigger data set. Okay. So from the documentation, text analysis is a major application field, blah, blah, blah. The raw data, a sequence of symbols, cannot be fed directly to the algorithms, as most of them expect numerical feature vectors with a fixed size rather than raw text documents with variable length. Okay? So you'll notice these are different length messages. They're not numbers. So those violate the two principles that scikit-learn is looking for. It needs a fixed size and it needs numbers. So we're going to use count vectorizer for the purpose of taking text data and converting it to numerical data. Okay, so that is the purpose. Its stated purpose is convert text into a matrix of token counts. Okay, tokens generally just means words. Doesn't have to mean individual words, but that's what tokens mean. We'll talk more about that in a few minutes. Okay. All right. So count vectorizer is what we're going to be using. So count vectorizer follows the same pattern that a lot of, well, not a lot, all scikit-learn estimators follow. So in the same way that you import, instantiate, and fit a model, you import and instantiate and fit count vectorizer. Even though count vectorizer is not a model, it has the same API, as it's known. It has the same API in that sense as a scikit-learn model. Okay, so don't get confused. Count vectorizer is not a model, but it has a fit method. Okay, so let's go ahead and import and instantiate this. So it's stored in a module called feature extraction.text, which tells you it's for feature extraction. And we're going to instantiate it with the default parameters and call this object, this instance, we're going to just call it vect. That's just my convention. We are going to talk about the non-default parameters later, but for now, we're just going to use the defaults. Okay. So import instantiate, next step is to fit. So we've got a vectorizer and we run a fit method and we pass it simple train, which is this list of strings that we've created. Okay. So I'm going to go ahead and run that, and you'll see the default parameters that it used. Again, we'll talk about that actually in the next class. Now, what happened? Okay, during model fitting, I pass it x and y for a supervised learning model. I pass it x and y, learns the relationship between x and y, right? So a vectorizer, the fit method, is when it learns the vocabulary. It learns literally what are the words being used, okay? So what did it learn? Well, once a vectorizer has been fit, it exposes a method called getFeatureNames, and we'll run that to examine what's known as the fitted vocabulary. Okay, so this is the vocabulary it learned, and let me just remind you of what the text was. Okay, so here's our raw text. Here is the fitted vocabulary. There are 5 things that I think are interesting about the differences between what you might have expected the fitted vocabulary to look like and what it actually looks like. So I'd love to hear from you. What are some of the things that may be surprising or at least are different than what you thought it might be? Amir says, why isn't A there? Okay, that's one of them. A is here, but it's not there. Great question. Zachary said no punctuation. Right, so you'll notice the exclamation point is not there, the spaces are not there, the periods are not there. Dominic, the list is alphabetical and Unicode. Great. So Vectorizer does return Unicode, which, well, we'll leave that alone for now. But yes, it put them in alphabetical order. Okay, that's not an accident. It is in alphabetical order on purpose. Amir, please and please uppercase are the same. Right. So it is ignoring case. Okay, so Amit and Prasad both mentioned that it appears to be doing stop word removal. Now, we'll talk about stop word removal next class, but I will say it's actually not removing stop words. It didn't remove A because it thinks it's a stop word. Don't worry if you have no idea what that is, a stop word. It's not removing A because it's a stop word. It's removing A because the default token pattern, if you can read escaped regular expressions, this is really ugly to read, but this is saying by default, drop words that are not at least 2 characters. So it's not removing stop words, it's removing anything that doesn't have at least 2 characters. Okay. Okay, great. So let's see, lowercase, no, yeah. You guys hit all the ones I was thinking of. So to summarize, the fit method of the vectorizer learns the vocabulary, and it learns it according to specific rules, and those rules are set up by count vectorizer and these arguments. Okay, so you can change the rules, but what I just showed you shows you the default rules. Joseph, the direct object of every sentence is in the vocabulary. It is, but it's only because it was at least 2 characters. So to be clear, vectorizers don't try to understand language. Vectorizers are there simply to extract, to convert text into a matrix of token counts. That's it. Doesn't understand that. It turns out when you exclude short words, you generally aren't losing much meaning, but you can be. So, all right. So that's the first step in vectorization. Okay. Now the next step is something called a transform. And I'll admit that when I was learning scikit-learn, transforms really confused me because transforms do different things depending upon the type of object. So fit for a model always means the same thing. Learn the relationship between the feature and the response, or unsupervised, I guess not. But transforms do completely different things depending upon the type of object that you're working with. So for a vectorizer, transforms whatever you pass it into a document term matrix. So let's look at it. So I'm going to say vect dot transform, and I pass it simple train. Okay, simple train, still just that Python list. Okay, list of strings. And it will return a document term matrix, which we'll see in a moment, and I'm storing it in an object called simple train underscore DTM, short for document term matrix. So let me run that, and it will say to me, this is a 3x6 sparse matrix. Okay, so anyone want to guess, or you may just know, anyone want to say why you think this is a 3x6 matrix? All right, boy, you guys are fast typers. Okay, so I've gotten like 15 responses here. Let's see. Thomas, 3 input samples, 6 feature names. That is a good summary. So 3 documents, 6 vocabulary words is how I would say it. Okay, now you might be thinking, wait, what's a document? Okay, so we know what so DTM, document term matrix. A document is a string, possibly with multiple lines, that you are giving to scikit-learn as a unit. Okay, so we're going to be in a little bit, we're going to be getting into spam filtering. And like, what is a document in the context of spam filtering? Well, a document would be, if it's email spam, an entire email. It would not just be a word from an email or a sentence from an email or a paragraph from an email. It would be the whole email. So that's what a document is in terms of a document term matrix. Now, it's your responsibility to pass it the entire email message as one big string so that it knows that is one document. So the short answer is, if you pass it a string of whatever length, it will count that as one document. And thus, when I passed it a list of 3 strings, it says, here's the first document, here's the second document, here's the third document. Okay? So 3 documents, 6 terms, also known as vocabulary words, also known as features, also known as tokens. Okay? I'm just going to scan through for questions real quick. And Alex was saying maybe I could give some examples of other documents. So email is one, but a book can be a document. Okay? So it all comes down to your task. Like, let's say I wanted to predict the gender of an author, of the gender of book authors. That was my supervised learning problem. Predicting the gender of book authors. What's my training data? Well, it's book and gender. So my X is the book, and my or books, and Y are the genders of their authors. Okay, so in that case, a book, the entire book, is the document. Okay, if I was predicting the tone, the sentiment of a chapter of a book, then the document would be the chapter. Okay, so it's whatever you define it as. A tweet could be a document. What type of text won't qualify as a document? Amir asks. There's no, it's up to you. So the answer, I think, is there's no text that can't be a document. A document is just the structural unit we're working with, okay? Dominic asks, do you always have to use transform with count vectorizer? Yes, and you'll see at the end of the pattern. Well, I guess you don't technically have to. There might be cases, I can imagine cases where you wouldn't, where all you want to do is learn the vocabulary of something and you just do a fit and that's it. So you don't have to, but if you're building models, the answer is yes. Manju asks, is this equivalent to samples/observations? Yes. So in the same way that you as the modeler define what counts as an observation in any model, you are deciding what is an observation, or a sample if you prefer that term. You decide what is a document. Okay. So this, I think, will all make more sense once we've gone through it a little more. But great questions. Love the questions. Okay, so I want you to see the end of this pattern before you forget what the start of the pattern was. So we did a fit with simple train. Then we did a transform with simple train and returned a document term matrix. Okay, so document term matrices have a to-array method. So we'll run that, and we'll see this. This is our 3x6 matrix as a dense matrix, not a sparse matrix. We'll come back to sparsity in a minute, but here's our 3 rows and our 6 columns. Now, let me go ahead and use pandas to examine these together, okay? And what I've done is I've just labeled the columns. Okay, so this is like the moment where I hope you're putting a few pieces together, which is, you see, it took text, which was non-numeric and variable length, and it's now representing it as a feature matrix with a fixed number of columns. That is what we were looking for. Okay? In the same way that we were happy that Iris always had, the Iris data set always had 4 columns, we like that we've now created a matrix that always has 6 columns. Okay, so what are these representations? Well, if you remember, the first message was call you tonight. So call you tonight. Call me a cab. Call me cab. And then please call me please. Please call me please. Okay, so it's literally just a count of the number of times a token appears in that message. Okay, so the scikit-learn documentation has a nice summary of this that I'll just read. So in this scheme, features and samples observations are defined as follows. Each individual token occurrence frequency is treated as a feature. The vector of all frequencies for a given document is a sample. Okay? So a corpus of documents, and a corpus just means a set of related documents. So we have a corpus of 3 documents in this case. A corpus of documents can be represented as a matrix with 1 row per document, 1 column per token /word /feature, all kind of the same thing. Now, again, tokens can have different meanings, but we'll get into that later. Okay, next class. So this is our document term matrix. Actually, this is our document term matrix, but this is the one I've labeled using a data frame. Okay. And one final thing here, we call vectorization the general process of turning a collection of text documents into numerical feature vectors. This strategy is called bag of words. If you're not familiar and you've heard people talk about bag of words and you're like, what is that? Sounds super fancy. Not really that fancy. Bag of words is this. Bag of words, and it's called a bag of words because, and I just, for whatever reason, I just imagine like a Scrabble, the bag where you like shake the letters and like, you pull out letters, whatever. The ordering is lost, okay? There's no ordering. It's like you put words in a bag and then you count them, but you've lost their ordering, okay? So, importantly, count vectorizer does not preserve ordering, okay, within a document, okay? completely ignoring the relative position information of words in the document. Can position information be useful? Of course. Maybe the first word of an email is more predictive of whether it's spam than the last word. I don't know. I've never studied it. But count vectorizer will not take that into account. Okay. All right. Let me see if there's anything else I wanted to mention. Oh, so I'm calling this a document term matrix. This is sometimes called a term document matrix, which is the same thing. But I like to say document term because in general, the convention in scikit-learn and NumPy and pandas is if you're describing a matrix, you talk about the rows first and then the columns. So if you look at the shape of something, it'll tell you the number of rows and then the number of columns. So I like to say document term matrix to remind myself that documents are the rows and terms are the columns. So DTM, not TDM. But if you said TDM, people would know what you were talking about. Okay, Vlad, what is the limit on the number of features? I don't think there is a limit. If there's a limit, I don't know what it is. It's probably just like a NumPy limit. How wide can an array be? I don't know, a billion? I'm not sure. But no practical limit that I'm aware of. Good question. Nick, preserve order to an extent if you choose n-grams of 2 or more, right? Yes, that is correct. We'll talk about n-grams next time, next class. But you are right. You will, to some extent, preserve order. You're exactly right. You're not really preserving like complete order, but you're getting more information potentially.